Hi, you've seen this painting before, way back in theme 1. This is James Hutton, the father of geology. He set out to try and work out how old the Earth was. This lesson is all about how our understanding of the age of the Earth has changed over time, and in particular with our discovery of radiometric dating. We're working on page 22 and 23 of the Theme 9 booklet. You should also have a colour version of the graph that's on page 23 to help you with this. Okay, on this diagram, I've given you the people who've tried to work out the age of the Earth throughout time. It gives an idea of what their concept was, and a little bit about the people who came up with these ideas. On the left-hand side there, I've given you a series of dates. Those dates are when those ideas were first published. So, for example, Archbishop Ussher there, using the Bible, working out who begat who, came up with an age of the Earth that was about 6,000 years old. And he published that in 1650. So I've linked Archbishop Ussher with 1650. What I'd like you to do, and you might want to do this in pencil to start with, is can you work out the dates at which these other ideas would have been published? Okay, you can see I've put the dates in time order to help you, from the oldest at the bottom to the youngest at the top. Okay, have a go at that, see what you can come up with. Press pause now. Okay, let me go through each of these methods. We start out with James Ussher, Archbishop of Armagh, who sat down ploughed through the Bible and tried to come up with the best interpretation of the age of the Earth, going right back to Adam and Eve, that he could come up with. And he came up with the, frankly odd, beginning of the night before the 23rd of October 4004 BC. It was a nice try with the best evidence he had. What's perhaps most remarkable is that some people still believe that to be the case. For a more scientific approach, we move on to the Comte de Buffon in 1779. He was trying to work out how quickly the Earth had cooled. And he came up with an age of 75,000 years, which I'm sure at the time would have seemed almost impossibly old. John Phillips then, a British geologist, was working on rates of deposition, looking in particular at the Ganges river in India, and how quickly sediment was deposited in the Ganges, and then trying to extrapolate that out to work out how long it would have taken for all the sediment on Earth to have accumulated. He came up with an age of 96 million years. Perhaps most famously, a very, very famous scientist called Lord Kelvin. The temperature scale is named after him. He was a Scot, and he was working on a scientific theory to calculate how long it had taken the Earth to cool from a ball of molten lava to the temperature we have now at the rate of heat loss that we can measure. And he very famously dismissed the whole science of geology by saying that Earth cannot have been old enough. He came up with an age of 24 million years. I think his maximum age, it could possibly be, was about 100 million years old. And he said that just simply wasn't enough time to for all these fanciful stories the geologists were coming up with about how old the Earth, about what had happened on the Earth. As it turned out, of course, he was wrong. Other scientists, John Joly, tried to work out the age of the Earth from how the speed at which the sea would get saltier. In 1899, he came up with an age of between 80 and 90 million years. Things started to improve somewhat in the 20th century. In 1913, a geologist working at Durham University called Arthur Holmes started to work on radioactive minerals in rocks and looking at decay rates. And with that, he came up with an age of 1.6 billion years, 1,600 million years. We're heading in the right direction, but clearly the method needed more refinement, and we also needed to find the right material. It wasn't until the mid-20th century, an American geologist called Claire Patterson, using these radiometric techniques, realised that dating Earth material wasn't particularly helpful for the age of the Earth, and he started dating meteorites. And he started to come up with an age that we now accept for the Earth of just over 4.5 billion years. So, if we fill in our diagram, we should see a pattern a little bit like that. Okay. So our understanding of the age of the Earth has changed over time. Perhaps the best way to look at that is this graph. This graph pieces together lots of published data about the Earth's age and looking at the method at which it was derived. So each of the different colours and symbols tell us about Earth age. We can see some really interesting information from this. You need to use the colour version that's been emailed out to you. But I'd like you to have a go now at the questions on page 23. Press pause, see what we can come up with. Okay then, let's see what you found. So I asked you to describe the pattern of our changing understanding of the age of the Earth. And we can see that as time has gone on, we've recognised that the Earth is older. So the more work we've done, the more the age of the Earth has been pushed back to older and older ages. If though we take a look at the radiometric ages, which you'll see here running through the 20th century, we can see how that pattern has changed over time. From the discovery by Holmes around about the time of the First World War of this technique of radiometric dating, there was, up until about 1950, quite a wide range of dates. The technique was still being resolved, it was still being determined, and we see quite a broad range of dates. All of them notice, or virtually all of them, older than the previous estimates. But it was only from the early 1950s onwards, after Claire Patterson's work, that we start to see a much more consistent set of dates. This is why we can be quite confident that the age of about 4.5 billion years is a reliable age from the Earth. Now, those of you that had to go at the digging deeper, will have thought about why the other things don't work. Erosion and sedimentation can't work to work out the age of the Earth because it's not constant. We have some periods where we get lots of deposition, other periods where we'll get very little. Not only that, but erosion will remove a lot of the evidence that we're using. So it can't give us a complete picture of the age of the Earth. The cooling of the Earth, like for example Lord Kelvin's attempts, were wrong because they didn't understand, they didn't know that the Earth actually generates its own heat. Radioactivity within the Earth releases heat. So the Earth isn't just a ball of magma that started hot and is now cooler. That heat has been generated throughout time, making the Earth's age significantly longer than it would have been if it was just a ball of magma that cooled to a solid. Okay, as we see sunset from the International Space Station, we can see that applying these radiometric techniques on the right material, in this case meteorites, gives us that consistent, reliable age of the Earth. We have to be able to understand about geological processes on Earth and why that means that actually dating meteorites is going to give us the most reliable results for the age of the Earth. Next time we need to start putting all of this together. I'll see you then.